Hi, I'm Zhiyuan Zhang. I will present this joint work, Global Context-Aware Convolution for 3D Point Cloud Understanding. The motivations come from the observation that most existing neural networks for point cloud is not rotation invariant. For example, the network may understand and process this aircraft model correctly in a specific pose. However, when the model is rotated, the network cannot properly understand the model in most time, because the network doesn't see the rotated pose during the training procedure. To resolve this problem, many methods rely on the data augmentation. That is, different poses of the models are added during the training procedure. In this way, the network can see many poses. However, the network trained with simple rotation augmentations cannot generalize well to unseen rotations. A few recent convolutions that allow rotation invariance still cannot achieve consistent predictions or not accurate because they lack global information. In this work, we designed a global context-aware convolution operator. Given this model as input, we extract key points indicated as red dots. For each one, we establish a global weighted local reference frame. The 3D coordinates of the key point neighbors are projected into the local space spanned by the frame to obtain rotation invariant features. To learn the global features, anchor points are constructed by averaging the points in each bin, which are used to approximate the global shape of the input model. Then the local and global relationship between the neighborhood points and anchors are explicitly encoded by computing the distances and the relative orientations. Followed by MLP and mass pooling layers, we finally obtain a 1 by C vector to represent the key point. C is the number of output channels. This feature vector contains both local and global rotation invariant information. For all the key points, we perform the same steps, and the output is like this. The dots with thicker shape indicate higher dimension, and we call this block as GCA-con. Based on the GCA-con operator, we can design the GCA-net, Global Context-Aware Neural Networks. The classification network comprises 3 GCA-con operators, followed by a classifier to output the class labels. It can also use for shape retrieval. The segmentation network follows the encoder and decoder architecture with skip connections similar to the UNet. It can also be used for normal estimation. To verify the rotation invariance ability, we conduct experiments and 3 training testing modes: ZZ, SO3, SO3, and ZSO3. Here, Z means ZX rotation, while SO3 means arbitrary rotation. ZZ mode is less challenging because the rotation directions are restricted, and in most cases, the training and testing poses are similar to some extent, while the ZSO3 mode is the most challenging scenario because the training and testing poses differ a lot most of the time. This table shows the classification results on ModelNet 40 dataset. The blue rows show the traditional non-rotation invariant methods. We can see that the results on the ZZ mode are good, while for SO3, SO3, and ZSO3 modes, the accuracies decrease a lot. The green rows are the recent rotation invariant methods, which output much more consistent accuracies across all the training and testing modes. However, the accuracies are not high due to the less discriminative features. Our method achieves the state-of-the-art performance with higher accuracies across all the training and testing modes, and it has a much smaller number of training parameters. The advantages of our method can also be reflected into the TSNE comparison between our method, PointNet++, and RCOM. The first column shows the latent space features and ZZ mode. We can see that both PointNet++ and our method have good separation, while the RCOM has more condensed clusters in the center. For ZSO3 mode, the third column, PointNet++ features are much more diverse, which cannot be used for point cloud analysis, while our method still has best separation. This table shows the part segmentation results on ShapeNet dataset. Our method still achieves consistent accuracies and the true challenging rotation mode. This is a qualitative result for part segmentation. It can be seen that our method is very similar to the ground truth, while other methods like icon, point purpose, and spiders in N differ from the ground truth a lot. Normal vector is one of the important properties of 3-point cloud data. We also conduct experiments to estimate the normal vectors on the ModelNet 40 dataset. We quantize the errors by calculating the angles between the predicted and ground truth normals. Our method achieves the best consistencies across all the 3 testing scenarios. In SO3, SO3, and ZSO3 cases, our method is the most accurate. In the figure, the blue vector shows the normal vector with errors less than 30 degrees, while the red ones show errors greater than 90 degrees. It can be seen that our method is visually the most accurate. We also verify the repeatability of the local reference frame, because it is the backbone for the proposed GC cone. We select 6 models from the Stanford 3D scanning repository, and the scenes are created by resampling the models down to half of their original resolution, with Gaussian noise added. The results are shown in the figure. The horizontal axis indicates the angular error range, and the vertical axis represents the percentage of points. The more points fall into the left lower range, the better of the method. We can see that our proposed LRFs have much more lower range angular errors than other methods. This means that the proposed LRFs are very stable and robust to noise. Please also visit our poster number 81 for more details. Thank you for the listening.